In this lesson, you will learn about how a system at equilibrium responds to changes in temperature. Le Chatelier's principle states that a chemical system at equilibrium always works to restore equilibrium when it is stressed. To consider what happens to a system at equilibrium when temperature is changed, you must first consider the energetics of the reaction in question. If the forward reaction is exothermic, then the reverse reaction must be endothermic. Let's examine this hypothetical reaction where reactant A reacts with reactant B to produce product C and product D, with a change in heat of minus 75 kilojoules. This means that when the forward reaction occurs, 75 kilojoules of energy is released and 75 kilojoules is absorbed when the reverse reaction occurs. So an increase in temperature would mean that the endothermic reaction would be favored to remove the excess heat, therefore counteracting the imposed stress. Decreasing the temperature would cause the system to produce more energy, therefore the exothermic reaction would be favored. When the temperature of a system at equilibrium is increased, the endothermic reaction is favored. When the temperature of a system at equilibrium is decreased, the exothermic reaction is favored.
Now the effective temperature is going to be different for an endothermic and an exothermic reaction, in that if temperature goes up, that means the endothermic direction is favored. The direction where heat is absorbed, that direction is favored. So an increase in temperature always results in a shift in the direction of the endothermic process. And that should make sense because if heat is absorbed, increasing the temperature is going to favor that because you're providing more energy, more heat. Now I said endothermic direction, and that's important because reversible reactions, such as this one, are endothermic in one direction and exothermic in another direction. So for this reaction, if I read it left to right, heat is a product. So reading left to right, the forward reaction is exothermic. If I consider the reverse reaction, so reading right to left, so that's the reverse reaction, that process is endothermic. So now if we consider this increase in temperature that we said was going to favor the endothermic process, that means that we're going to have a shift in the reverse direction, in the reverse reaction, so equilibrium is going to shift to the left. Now it's actually easier to treat heat as a reactant or product, just like we did with the concentration changes. So let's see what that looks like. Say I have a decrease in temperature. If I'm treating heat as a reactant or product, that means I have less heat. I'm removing something from the product side, so that means the product side is going to be less than the reactant side. In other words, reactants are now greater than products, which is going to give me a shift to the right. So this method works well for temperature and concentration, as long as we consider temperature as a reactant or product.
The dimerization of nitrogen dioxide to dinitrogen tetroxide is an exothermic reaction. Nitrogen dioxide is a brown gas, whereas dinitrogen tetroxide is colorless. What observations do you think can be made when the temperature is decreased? How about when the temperature is increased? Please pause the lesson to think about this and resume once you are done. A decrease in temperature favors the exothermic reaction, so more dinitrogen tetroxide is produced. Since it is a colorless gas, the mixture should appear paler. An increase in temperature favors the endothermic reaction, so more nitrogen dioxide is produced. The mixture should therefore appear darker brown.
So let's look at that same reaction. Again, we're taking this colorless dinitrogen tetraoxide and moving it into nitrogen dioxide, which is reddish brown. As we move from the left to the right side, that's going to be an endothermic reaction. What does that mean? It actually takes in heat from the surroundings as we move from the left to the right side. And so I'm simply going to add that heat down on the left side, and we can now treat it as a reactant. And so what happens if we increase the temperature? If we increase the temperature, if we increase that heat, what it's really doing is it's essentially adding more reactants. It's adding more things on the left side, And remember when we added more hydrogen in that Haber process, what happened? It switched to the right side. So we had a shift towards the right side. What's that going to do? It's going to push our reaction to the right. We're going to get a darker color. And so this is the same concentration of gas, but here and here they've heated it up. And so we're seeing that reaction move to the right side to counteract that increased temperatures. Likewise, what happens if we decrease the temperature? It's like decreasing the reactants on the left side, and now it's going to move towards the left side, and we're going to have more of that colorless gas.